Okay. Yes. Não, mas eu solto aqui o microfone sai. Quer soltar aí? Não, tem que desligar e tá. Solte aqui, solte aqui. Aí lá embaixo. Tá. Okay, let's see with the live. Yes.
Você conta no YouTube.
First semester class is always tricky with the setup. Let's see if we are already live over the faculty YouTube channel. These seminars are. Yes, it's working. Okay. I can hear myself. So welcome everyone to our seminar class in electrical engineering, second semester of 2023. And we are excited about having Harvey Newman from Caltech over here virtually, right? So in this connected world, we are hybrid. You can see some of the students that are joining us physically. We know many of the students that are involved or interested in the subjects follow us online or offline over YouTube. That's why we made the effort to try to record these guest talks about exciting topics in computer engineering, like the one that Harvey will bring us today about how to allow these data-intensive science exchanges of data through our compute and network infrastructures at scale, a demand that brings requirements that are higher and higher than ever, and that require advances in multiple areas, computing and networking, and that need to work together. These are multiple domains, technological, administrative, so a very challenging landscape. And Harvey and his group is the Global Network Advances Group, where we have collaborations in Brazil, in this worldwide initiative, are working towards the realization of these advances. So Harvey, please, the floor is yours.
We hope also to benefit other fields of data-intensive science and also be able to address other areas of society which deal with similar, very large data-intensive problems. So what you see here are some of the most data-intensive programs. On the left, the LHC, but there are also others, such as the big astrophysics projects, such as the large synoptic space telescope, which is now at the Vera Rubin Observatory in Chile. Also the Square Kilometer Array, which is being built and will occupy many millions of square kilometers in Australia and South Africa. And also the neutrino program at Fermilab, which has its own data-intensive challenges. So in meeting these challenges, I will talk about a group which has been formed in the last couple of years, the Global Network Advancement Group, and also try to make clear the systems approach to the whole set of problems which face us. So what keeps us going, first of all, is the scientific mission. I think you all know that at the Large Hadron Collider, the discovery of the Higgs boson was announced now about 11 years ago. And this has actually brought to an end a 48-year search, but we're in the midst of at least a 75-year exploration about the fundamental nature of matter, the forces between the basic particles, and also what lies beyond what we call the standard model, which encompasses all of the knowledge we have about fundamental physics in high-energy physics. One great thing about it is the discovery was taken not only as an achievement for science, but of humanity as a whole, that we came to understand at least some aspects of how nature is constructed and how particles in the universe acquire their mass. Since that time of the discovery, however, an amazing thing has happened. We thought we had ideas about what is the more fundamental theory. They turn out to be not true. At least nature is more subtle than our simplest ideas. So this exploration will go on at the Large Hadron Collider and at future colliders. The Large Hadron Collider and its second phase will continue until approximately the year 2042. So this shows that now we know that the Higgs boson is very much as predicted in the standard model, but we're trying to find what lies beyond. And one thing which has become a focus is to study the interaction of the Higgs bosons with themselves, which tells us about the shape of the potential, that what is the characteristic of the field in detail, which governs the interaction of the Higgs boson that forms all the masses of the elementary particles. So what we'll try to cover today, the challenges at the LHC and the next phase in scale and complexity and global extent. We've already come to understand in the last 2 years that the complex workflows and their scale is not fully captured in the requirements studies that have been done so far. And since 2019, we formed the Global Network Advancement Group, not only of the research and education networks of the world, but also leading science programs and also technologists who bridge the gap between engineering and science. The idea is to develop a system which is not only worldwide, but brings together and jointly manages computing, storage, and networks, all as first-class subsystems in this system. In meeting the challenges and trying to enable our community, knowing that the capacity of the world's networks is unlikely to be sufficient on its own, we need to make best use of the available capacity while accommodating traffic of other disciplines and even more, the much larger community of academics and research scientists and students who depend upon the world for their daily work, not only scientific work, but their work as a whole. We've launched many parallel lines of development, and we're starting to progressively integrate them into our system. And we've deployed at least 2 worldwide test beds, which I'll show you. In terms of basic scale, 100 gigabit per second links, which began on the large scale about a decade ago, are now moving more towards a commodity status. And we're starting to use 400 gigabit links nationally across the oceans and also on campuses. We're moving towards a very flexible software-driven architecture that needs to accommodate not only one set of tools, but actually multiple tools, because different world regions and different organizations, such as these science programs, have their own history, their own specific developments, and there are also multiple open source software approaches. What is the model concept? So I have one example, which is a data center analog, where the metrics of success take into account multiple dimensions: the priority of different flows and different requests for data, policy, network and site state, and approaching deadlines. And to deal with such complex metrics, we've also developed, in particular, members of our team, of our collaboration rather, from Géant in Europe and RNP, Marco Schwartz, are leading the move to develop a digital twin that enables us to simulate and emulate the system so that we can develop what's needed and then put it smoothly into production. Once such a system is deployed, it's really well adapted to be optimized using machine learning methods. And so one line of development involves machine learning to optimize large network systems. And finally, there's a very important development in Brazil, in Vittoria, the group at UFES in Vittoria, a polynomial key-based architecture for traffic engineering, which I'll try to cover towards the end. So when thinking about the LHC program at the beginning, around 1999, I envisaged this hierarchical setup where the experimental laboratory, CERN, has a large facility called the Tier 0, where there are national centers, of which there are now 13, called Tier 1 centers. And then we also invented the idea of smaller centers, of which there are now about 170, which can be operated and managed at the smaller laboratories and universities. And in addition, at the third tier, there are about 300 small clusters which serve individual physics groups. This very nice hierarchical picture was nice for explaining what we had in mind to managers. But in fact, scientists at many locations throughout the world simply need data and computational resources. And so it looks more like a cloud in some senses, where you can run any job anywhere. And we also have added to this picture the increasing use of external high-performance computing facilities and resources, because we need to acquire the largest capabilities that we can get in terms of computing and networking and also storage. That the world's research and education networks from the beginning of the LHC program have mobilized to support us and give us priority also in the way we use networks. There is a STAR network, which is called, for historical reasons, the LHC Optical Private Network. It's a STAR network in the upper left, where you have not only 100 gig links, but you're starting to see 200 and 400 gigabit links in there. But equally and more important are the national infrastructures, the continental networks in the United States and in Europe, and also now in Latin America, which I'll refer to, complemented by other national networks and also United States state networks. In the last couple of years, the contributions of the National Network of Brazil, RNP, and also the regional network in the Sao Paulo region called Rednesp have become very important partners in these joint developments. In terms of scale, if we look at what's called the worldwide LHC computing grid, which is used to share computational resources, and look at the data flows across it, you can see impressive growth. So you see on the left the plot of what the individual experiments at the LHC, CMS that I work on, a competing experiment on the same scale, Atlas, and other specialized experiments, ALICE and LHCb. And you can see that over the years, the flows have grown. So recently, we've seen flows of 30 to 85 gigabytes per second as a weekly average, sometimes a daily average of 100 gigabytes per second. And these are very complex workflows, up to 1.3 million jobs executing simultaneously. There are transfers which are often multiple terabytes and occasionally petabytes in size. One thing you can sort of see around 2020 to 22 is what happened with COVID, a temporary decrease in the traffic. But as soon as we really started to recover in 2022, a very rapid recovery. And now we're at and above the levels of data flows we experienced before the COVID years. And this also makes it clear. I sort of divided up the years into periods to see how much growth with respect to the beginning of the last major run, called Run 2 at the LHC in 2015, how much growth we experienced relative to that level. And you see it growing fast until 2020, then a temporary drop, but then a very rapid resumption of the large flows. And here also, if you look at CERN in particular, you can see that what's very impressive over the last 2 years when we started the third major run of the LHC, which started in 2022 and will continue through 2025, that the average growth was quite substantial, but the peak growth, the peak traffic really has risen at a very large rate, 3.5 times in 2 years. It's telling you that within an affordable budget, we cannot just rely on what's called over-provisioning to have enough capacity to meet the needs of this program. Apart from scale, the other problem is complexity. What was formed, again, I helped originate this in 2011. The LHC open network environment is what's called the virtual routing and forwarding fabric, which favors the admission of traffic only from sites and facilities which are participating in the science programs. It started with the LHC, now other major hydrophysics programs are also allowed. Now it spans more than 60 domains throughout the world, and you can see that the overall system is very complex. So we have to deal with this complexity, and it's another part of the overall challenge, apart from scale. So looking forward towards the high luminosity LHC, it really crystallized the idea that we have some very important challenges and we have to take systematic action. At the beginning of 2020, the LHC experiments had a meeting and put forward the fact that for the next phase, for the high luminosity LHC, which is now being constructed along with upgrades to the experiments, that we'd have to support terabit per second links on the major routes in many areas of the world by around 2029. This was laid out in some systematic requirements document studies. I show a link there for those who want to look into that, which shows the needs not only of the LHC, but other programs. This was conducted by the Energy Sciences Network in the United States. We already know, actually, that in the 2-year update, which is taking place now, that the flows now, we understand, are somewhat bigger than the 2021 requirements estimates we had just 2 years ago. There are 3 areas of concern coming out of this study. One, clearly exceeding the capacity across oceans, notably the Atlantic. There's a consortium of network organizations which is doing that, and they're trying to support us, but we have to also be co-developers of a system that allows their operations to coexist with what we're doing as partners. But also universities. I mean, when we look at what we do now at the Tier 2 centers, which are typically hosting 5 to 10 petabytes of data, in the next cycle, in the high luminosity LHC era, it'll be more like 30 petabytes. And the typical operation would be to exchange a petabyte in a ship, which means pretty much you need a 400 gigabit link as a baseline. And then, as I mentioned, terabit per second links to the labs and external HPC centers. So apart from that, you can also think about the physics. At the high luminosity LHC, not only will the beams be much brighter with more interactions, more billions of interactions per second, but also the detectors are more sophisticated, and therefore the data flows just from their complexity also goes up. So in terms of the primary data volume per year, we're going to face about a factor of 30 relative to the present run. Some actions that we took, we tried to foresee what's called the data lake model, in which centers, like the leading example is Caltech and UCSD in San Diego, could treat themselves as a single facility, although they're physically separated. And to use these as joint caches to reduce the number of copies of the data which have to be supported. And in doing that, we also thought of a critical distance like 500 kilometers, where the round trip time over networks is not such that it degrades the performance too much, so that we can actually foresee this kind of joint caching throughout regions of the world. And the example of just a high-level concept for Europe as an example. Also, we have to foresee how we're going to develop this system operationally. And the present director, my former colleague, he used to be in this next office from me at Caltech, now the director of the San Diego Supercomputer Center, has envisaged this kind of sequence of challenges, where first, functionality challenge, build the software stack to manage these large data flows and also deal with competing requests, software scalability, scale it up, and then use the final hardware. The first of these challenges in a simplified form already occurred at the 10% level compared to what will ultimately be needed. The next one will be a real challenge at 25%, which would mean about 250 gigabytes per second or 2 terabits per second, which is coming already at the beginning of next year. And as it says in the middle, it's conceivable and even probable that it'll take multiple attempts to succeed in building this system. Now, this just lays out the fact that what has happened in terms of our concern for data flows across the Atlantic in particular, when adding up the requirements in a minimal model in the 2021 study, the requirement overall was 4.8 terabits per second. And that included about 1/4 of it across the Atlantic just for Atlas and CMS, the largest LHC experiments. But in a more reasonable, flexible model where you actually include reprocessing and reconstructing the data as you learn to improve your software about every 3 months, that about doubles the requirement and includes 2.7, it should say terabits per second across the Atlantic just for Atlas and CMS alone. And even so, other things like simulation production, simulated data, which is very important, is not yet included in those models. The world's research and education networks, and in particular, the US National Network Internet 2, the Canadian Network Canary, the Energy Sciences Network, together with partners in Europe, GNA-G in particular, have begun to field transatlantic 400 gigabit per second links. The first link between New York and London is already in operation. The extensions to CERN are underway and should be during this quarter that we start to see them. And also other exchange points in the US, in Boston and another city to be determined, and also other cities in Europe. It's hoped that by the Data Challenge 24 early next year, there'll be 1 terabit per second capacity across the Atlantic and 3.2 terabits per second in advance of the high luminosity LHC. If you remember the numbers, given the needs of this program and the worldwide needs, it says again that it's very good that the research and education networks of the world have done this, but at the same time, we have to develop this more sophisticated system to manage it all. So it's against this backdrop that this Global Network Advancement Group was formed. A volunteer group first to bring together network resources to make the global R&E networks both simpler and more effective by working together, supporting research and education globally, but also to participate in enabling not only high-performance data transfers, but also being a partner in the development of next-generation intelligent network systems that support the workflow of the programs that we saw. One thing about it is truly global, and this is really impressive and important. You can see consortia which are brought together within the framework of the Global Network Advancement Group across the Atlantic, the Asia-Pacific Europe Ring, the Asia-Pacific Oceania Network across the Pacific, and very important also the links within Latin America and between Latin America and the United States to Europe and to Africa. Among these, a very important development which just occurred in the last year was the rise of Rednesp, this collaborative network for the Sao Paulo region, which includes multiple 100 gig links between Brazil, the United States, and also Europe, together with RNP, the National Brazilian Network. And also, very important are the links to the important universities, not only in the region, but but adjoining areas. And I put first among these Unicamp, your university of Campinas, and these were successfully completed by last May. As I said, it's truly global. There are also important links across the Pacific, and another important partner is KAUST in Saudi Arabia that we're working with. And another research project across the Atlantic, which is new, is called Bridges between the United States and Europe. All right. Now, the working groups within the Global Network Advancement Group are very important, but if you look carefully, you'll see they actually have two sides. On the right are production operations. For example, there are about 200 engineers who study routing anomalies to track down problems with routing and therefore general network performance problems, and also problems of security, network automation from the production network point of view. On the left, we have very important research and development, in particular the Data Intensive Science Working Group that I founded in 2020, and another one which I participate in called the AutoGOLE Sense Working Group. And I drew this arrow between the two, and this relates to that digital twin, to be able to do these advanced developments and through techniques such as the digital twin to progressively bring the products of those developments into wide-scale production. So our working group, as you heard, principal aim is to address the challenges of the major data-intensive science programs, but in a way that's compatible with the wider continuum network operations. Also to provide a forum for discussion and a framework and a shared tool set for both short and long-term developments. In doing these developments, we have a number of concerns to address the growing demand for network integrated workflows, that is, workflows that bring together networking, computing, and storage, to manage data and also bring to bear the facilities at many sites in different world regions. Automation is extremely important. And what are called federated infrastructures that bring together heterogeneous software stacks and services, but in a way which is mutually compatible. And so this is a very large worldwide partnership, and you see some of the members, including a member from Brazil. You recognize people from Rio, Sao Paulo, and UFES, and I just wanted to emphasize here that Unicamp is very welcome to join. In fact, we really appreciate it. We meet weekly or bi-weekly, and everybody is welcome to join. And you also see some of the network and science programs and universities which are in this working group. Now, one thing is advanced technologies. This is just a cartoon I made about a year ago to show what's happening in Los Angeles. And you can see, if you look carefully, you'll see the point of presence in Los Angeles is connected to Caltech and to University of California, San Diego by 400 gigabit aggregate links. At SC22, the supercomputing conference in 2022, we had 400 gigabit links to Dallas from Los Angeles. Now this year, we're going to have 3 400 gigabit links to Denver, where Supercomputing 23 is cited. And Caltech, together with Scenic and Sienna, are working on the use of a dark fiber with these so-called pluggable transceivers which fit into switches, which don't need a separate optical platform, which will support 400 gigabit waves over the metropolitan area distances direct to the campus. So the first time, we'll essentially have these multiple 400 gigabit links coming directly. It'll look direct from Denver all the way to our group on the campus. Now, one of the key things is that, as I mentioned, that until now, the network has looked like an opaque infrastructure. Even people who are really familiar with computing and storage, they often feel that the network is a kind of a formless entity that's external and just wish for sufficient capacity. But in fact, we have to treat this, as I said, as a system. And so our working group and our adjoining working group, the AutoGOLE Sense working group, is working on the key ideas in order to be able to manage the infrastructure. So this project is able to create virtual circuits with bandwidth guarantees across multiple network domains, and they're developing control plane monitoring and also the data plane. So a study and design group has been formed, and it has multiple projects which are taking advantage of this, including some very large ones like Fabric, which is a major project funded by the U.S. National Science Foundation, Qualcomm Technologies Gradient Graph, which I won't have much time, I see, to get into, and a number of others. So the idea is that this system, this project Sense, is sitting between the SDN layer, the software-defined network layer, and the workflow agents of the science programs. And the workflow and network can interact for planning, resource discovery, negotiating, capacity, and full lifecycle monitoring of transactions which are going on. And you can also schedule the workflows and also decide on what gets how much resource and relative priorities. We have fielded a global test bed in association with this working group, and you can see here sites within this test bed in the Middle East at KAUST, in Japan, in Taiwan, also Guam and Hawaii. Then apart from the US, you see important sites also in Latin America. The Bella link between Latin America and via Empath to Europe, and also Netherlight in Amsterdam and CERN. And then in the top, you can see sites in Korea and then Singapore. So the idea is not only to make these overlays with bandwidth guarantees, but also, very important, to integrate with the main data management software and systems which are fielded by the LHC experiments. And that's really crucial. And there are certain tools for doing this called Rusio, which was originated by the Atlas experiment. FTS is the file transfer service, and XRUD is a federated access protocol, which is used widely, not only by the LHC, but overall by about 30 data-intensive programs. And this shows some of the programs which are using this paradigm of FTS and Rusio and XRUD. How it works, I won't have time to go into. This shows how, if you look afterwards at the slides, you'll be able to follow the various steps which go into this overall process in my slides. We already succeeded in using this production software setup to achieve 400 gigabits a second over short distances between Caltech and San Diego. And the next step is to include more sites, including the Tier 1 center at Fermilab and some of the other Tier 2 sites, using our regional network in California, but also Energy Sciences Network. And we expect also to include CERN either this fall or early next year. In talking about this management, I mean, we don't really need to know about every flow, but we need to identify flows which either have high priority or as a group need special treatment or are underperforming. So we need to be able to manage any flow or any group of flows. And this shows a picture of what we envisage to do this over some of the links across the Atlantic. So I also wanted to mention an initiative led by Marco Schwartz from RNP and Frederic Louis from GEON, which is the Global P4 Lab. The idea is, given the system demands, how can you develop and operate multi-domain orchestration services to make such a system possible, including aspects of resource reservation, provisioning with virtual circuits, or like in LHC1, virtual routing and forwarding fabrics, being able also at the application level and the higher network levels to really understand what's happening in the underlay in the infrastructure, and to do with this knowledge, to do your dynamic traffic steering and engineering, and to create virtual private networks and so on. And so in order to study this and develop this, we focused on P4. I won't have time to go on why we picked P4. It actually is an entire ecosystem. We also learned that since Intel will not continue to make their chips, called Topino chips, in the third generation, we also have generalized to have a broader view of programmable networking, not only the P4 programming language, but the network programming language of Broadcom and other tools and core services as part of this picture. Again, there is a global testbed. This is the global P4 testbed, which now has about 30 sites and more, which are coming, including important ones. And you see in the middle, site Southern Light, all the sites on Southern Light, Red Clara, Rednesp, RNP, and an increasing number of sites in Latin America. And this provides a sort of global playing field for next generation network development, fully automated network deployments, and to be able to accommodate multiple software stacks to federate and integrate multiple testbeds and tool sets, such as AutoGOLE Sense, as well as others. And I already mentioned the digital twin, which is a high fidelity emulation and simulation of the actual network topology with a smooth transition from simulation to real-world global network operations. So overall, this architecture has various important aspects to achieve this. Some of the main lines of the architecture are to have rather unprecedented levels of visibility, end-to-end monitoring, and you can see a list of some of the many tools that we use, and some of them we're actually developing ourselves. Intelligence, so we can have stateful decisions with composable metrics. Like I said, policy, priority, network and site state, approaching deadlines, so you have service level agreements which are coming to bear, and responses to events at sites and in the networks, and we have multiple tools there. Controllability with virtual circuits, with P4 programmable networking, various forms of segment routing. If I have time, let's see. I'm getting short of time here. I wanted to cover Polka also and other tools, and multiple network operating systems, and also means of orchestrating it all, Sense, but also Kubernetes and the Kubernetes namespace and other dedicated tools and code. Now, I also mentioned my architectural model, a data center analog. Imagine you have all these sets of requests coming in, different priorities, different policies, different parameter sets characterizing the transaction. How much data, for example, is it? How much resource am I committed when I respond to this request, say for a set of data transfers? So it has classes of work, like a data center with different queues. It adjusts the rate of progress in each class. It moderates, balances the rates among the classes. And then it's able to optimize, this is the plan, optimize a multivariate objective function with constraints. And like I said, the overarching concept is to be consistent with the needs and the network flows of the much larger community that depends upon the world's networks. So there's work, for example, in ESNet by computer science Mariam Kiran, who's now moved to the Oak Ridge National Lab, projects on self-driving networks, where one can learn how to do adaptive routing to avoid congestion, move towards 100% utilization, and also have proactive fault repair. So there have been various case studies, model-free techniques such as reinforcement learning to learn how to optimize path selection for large data transfers and better load balancing. Another model-free study on forwarding decisions for complex topologies, to learn optical packet delivery policies, for example, reliability and or maximum throughput, and model-based ones that predict network patterns so that one can foresee what will happen in the patterns of flows and how to manage them as a whole. So various interesting techniques have been used. One of them is this distributed diffusion convolutional recurrent neural networks. This is a means of doing spatiotemporal forecasting, which has been used to predict real traffic in the LA area, but also has applications in neuroscience, in predicting climate, smart grids, logistics, supply chain. And there's a link to a paper. And also intelligent network engineering. She's done a simple model, but it has hooks for much more stateful objectives. And I can show you that for a moment. This just looks at a set of links in a topology on ESNet, the Energy Science Network, and moves flows. The links get heavily loaded, moves those flows onto less loaded links. You can see the colors changing, indicating how heavy flows are dynamically changed to other paths. I wanted to say a little bit about supercomputing. It's really been the field in which we have been able to show some of the large-scale system-level developments. Already in 2015, we received the first 29 of the first 100 gigabit per second network interface cards. Since 2018, we've been building terabit per second rings at the site. But now you can see that we're also starting to do this on a very large scale over the wide area network as well. And these are vast partnerships demonstrating a wide range of advanced developments, some of which I already mentioned. You see them summarized again here. So this is the picture for SE23. You can see in the background LHC1, but then you see superimposed some of the major links between Caltech, the Starlight facility in Chicago, the supercomputing venue, which this year will be in Denver, and the very thick lines are 3 by 400 gigabit links. And like I said, including a direct link planned to the Caltech campus. So finally, Polka, very important development by Magnus Martinello and his group, together with other groups, and also involving myself. And what's so important about this is, if you have what's called source-based routing in networks, then you can have a stateless core. Namely, you can determine paths, routes, and then hop by hop without actually requiring state changes in the center of the network as packets go from one switch to the next along different links. The source-based routing, the segment routing, which has been developed commercially, doesn't quite have a stateless core because it has a whole series of user-defined labels, and every switch needs to have hardware to be able to pop the labels, identify what is the next port, and do this at wire speed. This is all bypassed by this very groundbreaking and clever technique. A single user-defined label is encoded and decoded using the residual number system, polynomial residual number system, and the Chinese remainder theorem. This is something that even a freshman that I worked with at Caltech as a math major knew about. I presume many of you know about. The point is that you can encode this single label, and then you have for each switch a so-called node ID, and you can use the mod operation, look at the remainder after division to determine the port ID. So you have a route ID, and then if you take the node ID as the base to do the mod operation on the route ID, you get the port ID. And if you think about it, these mod operations really have to do with masks and shifts, and these are very fast in general in hardware. And in addition, they take over the switch, the hardware which is used in every switch for cyclical redundancy check. And so it's been shown to work well at very high speed. Having a stateless core means easy setup of paths and tunnels. And there also is an open source implementation in the open source operating system developed by Jayon together with RNP called FreeRouter. And so there are many powerful network applications that before was very complex, what's called proof of transit, policy-based routing, multipath or multicast topologies, failure protection and failover, inline telemetry, and so on. So this just shows how it works. You calculate a route ID as a series of polynomials multiplied together, then as a packet. When a packet is injected, the controller installs flow entries at the edges and removes them at the end, so that apart from this architecture outside in production networks, it's transparent. And then you have, like I said, port ID is the route ID, modulo the node ID, and that's it. So this was shown at SE 2022 in our lab at Caltech between 4 programmable P4 switches at 100 and 400 gigabits per second. And they're also first demonstration of dynamic traffic steering in an intercontinental test bed. And now for SC23, we're moving on and want to investigate 2 things. One, scaling up. This is a picture again of our test bed, so let me skip over that for the moment. Now, it was tested up to 100 gigabits a second. Now, right now, we have a target rate of 300 gigabits per second in our test bed, and then prepare for SC23 at 100 to 400 gigabits per second. And then to use the global P4 lab, this is under development, to be able to show dynamic routing and traffic engineering in a global programmable test bed. And another addition is that traffic engineering decisions can be guided by mathematics. And in particular, there is this quantitative theory of bottleneck structures, which was developed by a company called Reservoir Labs, which is now part of Qualcomm Technologies. And this bottleneck structure, mathematics and software, is called gradient graph. So that's it. The top line message here is that to realize the physics discovery potential and meet the challenges, not only of the high luminosity era, but in general, for data-intensive science programs, we need a new dynamic system which coordinates worldwide networks as a first-class resource, along with computing and storage across and among world regions. To do this, you have to follow a system design approach and deploy a global fabric that flexibly can allocate, balance, and make best use of available network resources, negotiating with site systems that aim to accelerate workflow on behalf of the science programs, that builds on many R&D projects. I showed you many of them, from regional caches and data lakes to intelligent control and data planes to machine learning-based optimization, that leverages the worldwide move towards a fully programmable ecosystem of networks and end systems, multiple network operating systems, source-based routing like Polka, and operations platforms, the Open Science Grid, the National Research Platform, and the 2 global test beds I showed you from SENSE and the global P4 lab. And simultaneously supporting the LHC experiments and being compatible and in fact helping the operations of research and education networks in their mission to support the larger academic and research community. So you can see that the science programs and working together with research and education networks and the framework in particular, the Global Network Advancement Group is one of the central elements and enablers of this whole mission and this whole development trajectory. So that's it. Thank you.
You done?
Yes. I don't, well, there are leading problems, but I would not look at it as just a barrier to be overcome. It's a set of problems which we need to overcome. So first of all, is the fact that this is a worldwide system, so we need to accommodate developments and the history and standards in multiple world regions. That's one thing. But when I think about it, if we manage to have a certain degree of success, this has very profound societal benefits, also in terms of global cooperation. Another one is clearly simpler. It is funding. We are a big volunteer group. It's an enormous mission. But at the same time, you can get the feeling, as you heard me go through this, that it's difficult to comprehend. There are not so many people who can comprehend not only the aspects in this mission, but also the fact that it is practical to attack this set of problems with a very good chance of success.
So you need folks like some of the collaborators that you have mentioned that are multidisciplinary, so they understand from networking, from compute, even from the experimenter perspective. Yeah. I think this one breaks silos, traditional silos, and the ability to have professionals, collaborators that understand the multiple views and are able to see the gaps, and I think to me this is a type of educational training type of gap.
Yes.
As a main challenge, right?
I think you really got it. You really got it. And how to say, there are not so many people. And there could be more of them. And training more people like that would also have a very profound impact in terms of not only this set of problems, but in the nature of problem solving in many areas, you know? Mm-hmm. And so we deal, you know, in this case, we deal with really multiple layers all the way down to the, you know, the newest transceivers and switches and how they work up to the global system level. And also not to be afraid to attack this whole set of problems.
Yes. Okay, let me check if we have 2 more minutes. Is there some question over here in the chat room? No? Yeah, I think they are afraid. So much content. So I think for the first seminar, they may be afraid. Let me check online in the live chat if there's some question. Hold on. Live chat. Okay. I suspect Marcos Schwartz is following us. How can new Brazilian networking research groups start contributing with this global effort? So what's the entry point? Someone watch this talk, feels inspired, there's a way of contribution. What is the entry point?
Yes, you know, I mean, in any large project, there are current problems. So, I mean, there are 2 examples related to the 2 global testbeds. Within the SANS architecture, there is a component called the Data Movement Manager. This is the place where all the monitoring information comes, and using that monitoring information, you can make decisions, which, like I said, can, you know, start simple but become very sophisticated decisions, balancing different, you know, requests, and so on. We don't have that code yet. You know, a smart person can come in, can just learn a little bit about the general context, and then can start working on that code. The other one I think is also similar, and it's great that the question came from Marcos. In the global P4 lab, I really didn't have time to spend enough time on those couple of slides. But, you know, where they are now and the next sort of round in actually dealing with the higher layers and decisions in a programmable network, a lot of that work has not been done. So you don't have to do everything over, but you can enter at a very important place and learn what needs to be done. Then you learn a bit, you know, you follow tutorials about P4 and programming language and so on. But there are people around you to support you in terms of infrastructure, in terms of services, you know, with known APIs and interfaces. And so I think there's plenty of opportunity for smart people to get involved without being overwhelmed. But as you indicated, it's important not to be afraid.
Yeah, great, Harvey. This
Yeah.
has been great. Thank you again for your availability for the great content. We really need to cut short.
Yeah,
We
thank you
chose
so much.
this slot. It's in the middle of our Brazilian between classes after lunch because we want to have as much as
That's very good.
participation. Thank you again. The messages are clear. These are big opportunities, big challenges. The doors are open for contributions
And a person can make a difference.
yes, so impact, chances for opportunity, education, multidisciplinarity.
Yes.
I think all these were great messages. So thank you, Harvey. Looking forward to meet
It's
you.
a pleasure.
Take care.
Okay, I hope so soon.